still have all the latency that we talked about, but the other 31 bytes will have minimal latency. In fact, as a processor, I'm going to synchronize with the memory chip, and I will say, look at the memory clock, okay, which is an ongoing clock that's always at a certain frequency. I'm just telling the memory chip here, okay, I'm assuming you can keep up with me, okay? But every time you see an edge, whether it's a rising edge or a falling edge, you have to sample the data line because it's a new data on that line. And then every time you see a clock edge, you also have to remember to increment the page number, because every time you see that clock edge, it means flip to the next page and then sample the data line and write to that location. But I'm not going to specify the entire address anymore. So any latency associated with addressing an arbitrary location is gone. And that's how we can pump data really, really quick using this particular mode. Now, how does that have anything to do with cache? Well, when you're caching, you're not caching a byte by byte basis. Caches or a cache is organized by quote-unquote pages. In other words, we are not just remembering on a little notepad here and say, oh, you just wrote to location da da da, and that's the content of that one byte location. We are keeping multiple locations on one cache page. So when we need to refresh cache, when we need to flush cache so that it writes out to memory content, we are writing 32 bytes at a time. And that's why SD-RAM is useful when we're using cache, because we are no longer writing byte by byte. Every time we write, every time we read, we're always reading in quanta of 32 bytes in this example. Okay? And that's how we can speed up memory access. But this doesn't help certain types of program, because if your program is random accessing single bytes all over the place, then nothing helps. Nothing that we talked about is going to help, because burst mode access is not going to help. The cache is not going to help because you're infrequently accessing those locations. Caching only helps when you're accessing some location frequently. Okay, you keep accessing the same thing over and over again. But if you're accessing things, all kind of at random locations, the cache is not going to be very helpful. Okay. Are we doing okay so far with these concepts? For those of you who have taken cisp310, did you guys talk about sorting algorithms?
Yeah.
Okay. Now, different sorting algorithms have the same time complexity. Did Mr. Fox talk about time complexity?
Log n.
And log n is as quick as you can do it with sorting, right? Okay. So you get quick sort, you have merge sort, you have heap sort, okay? Now, some of those are particularly friendly to what we just talked about, burst mode access and also caching. Can someone think of one sorting algorithm that is particularly friendly to this type of thing? Think sequential access, okay? Which sorting algorithm tends to access the next one, the next one, the next one, the next one, instead of here, over here, and over here, over here, and over here?
Insertion sort.
Insertion sort is linear, okay, but insertion sort has a time complexity of n squared.
Bubble sort.
Because of that, it is always going to lose the time.
Bubble sort.
Bubble sort is the same thing. It also has a time complexity of n squared. So you have to select from sorting algorithms that only has a time complexity of n log n.
That be merge sort?
Sorry? Hash. Hashing is only good for lookup, not for sorting. Okay, how many people still remember merge sort?
Merge sort, yes.
Yes, it is merge sort. Okay, merge sort is our winner. Okay, now the reason why merge sort is particularly friendly to SD-RAM, burst access, and also caching is because it has a lot of locality. Okay, because you're always accessing the next location, the next location, the next location. You only have 3 arrays, right, or 3 streams. And you're only accessing the streams in one single direction. It's not random access. Okay? Can anyone imagine or think about merge sort, about its original application? Somebody made fun of that word a little bit earlier, and now it's coming back to haunt us.
Merging files.
No. tape. Remember tape? When I say tape archive, you were kind of chuckling. Okay. Merge sort was an algorithm that worked really well on tapes, because you need 3 tapes, right? When you're splitting, you have 1 incoming tape and you write to 2 different tapes. When you are merging, you're reading from those 2 output tape, the previously output tape, and then you merge it into 1, and then you flip again, right? So you only need 3 tape reels for merge sort to work. And yet it still has a time complexity of n log n. And how much memory does it need with merge sort? If everything is stored on tape, you only need to store 2 records, right? Maybe 3, okay, 2 or 3 records. That's all you need to store, because that's all you need to compare and say, okay, this one has to go to this tape, this one has to go to this tape, this one can continue with that tape. Oh, okay, we cannot use that tape anymore, now we switch over to this one. Okay? So that really kind of gives you the perspective of these, sorting algorithms. Because you look at merge sort, it looks kind of clunky and ugly. It's very ungainly, right? You look at quick sort, it's cool. It can be recursive and all the other cool stuff. But when you try to perform quick sort, all this stuff is out the window, because it has a lot of random access all over the place. It's not linear in any particular way. And it's also recursive. As much as Mr. Fox will convince you that recursion is your friend, sometimes it is not your friend.
Well, can't merge sort be written recursively? I mean, merge sort can be written recursively, right?
Anything can be recursive, anything can be iterative. The 2 approaches are equivalent. You give me anything that is iterative, which means it uses a loop, I can turn it into recursive.
Well,
you give me anything that is recursive, I can turn it back into iterative. Okay? So the question is, which way is a better way of looking at things, and also, what are the limitations of your system? Recursion has one big problem. Okay? It is using a stack, and unless you know exactly what is the deepest level of recursion, the amount of stack that it is going to use is undetermined, okay? Because it depends on the input. Now, that normally is not a problem when we have super duper computers with 16 gigs of RAM and lots of stack space, and so it's not typically a problem, right? I'm just picking on you, I'm sorry. But it's a whole different story when you're working on a platform that has a very limited amount of RAM and is controlling a robot on Mars, right? So in embedded systems, especially the ones with limited resources, we avoid recursion like a plague. Then the next question is, but what about these algorithms that are recursive? Well, as I said, anything that's recursive can be turned into non-recursive iterative algorithms. You do have to maintain your own stack. You're using your own stack pointer. If the problem is too big and you're running out of your internal stack, at least in that case, you have a chance to catch it, and then you can say, okay, I cannot continue with this algorithm, and then you can figure out something else to do. If you crash the system stack because you ran out of stack space, you're done for. That robot on Mars, it becomes e-waste on Mars. Okay, so recursive algorithm is elegant, it is useful, it is really good for expressing certain types of solutions. But at the same time, because of the recursive nature, it uses up the stack, and we will see in this class how the stack is used in a recursive algorithm. Recursive or not, okay? Any type of subroutine, will use up stack space.
How long does it take to actually get a remote signal to Mars to control the rover? 16 minutes?
It depends on how the Earth and the Mars relate, because we can be opposing, the sun is in the middle, or we can be right next to each other, right? And what do you guys feel like, having the Mars rover to have to do garbage collection, like in Java? It moves along, and then go like, oh, garbage collection. And it moves along again. Well, it depends on the garbage collection algorithm. Some can be non-intrusive or as intrusive as we think. All right. So we are running out of time. For those of you who are kind enough to help me with load balancing the class, we are going to room 126, and I'll give you the forms. If you want to do the homework assignment tonight, go ahead. I think it's a good idea to get it out of the way. So we are moving to room 126 right now. I'm going to shut down the system and then move.
Iteration's always faster.
The only reason why Dave says